Okay, now we build our model. So let's fire it up. So I meant to put in a text cell here. Let's call it maybe CNN model. Notice the subheader because we're already inside of CNN. All right, so I'm going to modify, excuse me, what we already have here. And what do we actually need? Well, I can tell you that what it is, it's a layer and it's called conv2D. Look at all the convolutions here. So conv2D is standard. We're doing two-dimensional convolutions. And the other thing is we want to flatten them at the end. That is also standard. Okay, so dot flatten. And then we'll look at adding in some max pools. And we're going to use the dints as well for the y output. Because talk about why is not the input? Why is not being what's being convolutioned, if you like? Why it's already in the right shape for the output. That's why we don't reshape it. Okay, so cleaning up previous code. We don't need this. You do still declare it actually as a sequential model. All right. What happens though, it's what we're going to do here is add the convolution. Okay. So add a convolution layer instead of like it means is it hidden? Well, it's a convolution. So let's just take that out. And do note, by the way, that the output is still right here. Okay, it's still going to be like going right to one of the 10 numbers using softmax. So how do we do the convolution layer? Well, like usual, it's model.add. And then what do we put next? We'll just think about what did we add in, right? Conv2D. So that's what we need. Conv2D. Okay. And now inside of parentheses, we give it the inputs. And the first input that we want to give it are the number of, you could call it like maps or the number of filters, right? Like how many different convolutions do we have? If you recall that one image, right? It's not enough just to do one convolution. You know, we want high level, low level. Let's not go crazy. Let's try 32. Okay. Next, I like to do kernel size. So you can write kernel underscore size. And what that will do is like, are we doing 3 by 3, 2 by 2? You could go higher and do 4 by 4. I like 3. So let's do a kernel size of 3. Okay. Next, we'll set up an activation of ReLU, standard like before. And now we need the input shape. Okay. So what's the input shape here? Right? These are always like a little bit tricky. So if you think back about what it was before, that may help here. Like it's not, and we've got X shape. Is it just this? Well, it's actually not the 2000, it's the other pieces. It's basically the 28 by 28 by 1. So let's just put that in there. 28 by 28 by 1. And it has to do with the way models are structured, right? They're structured for kind of like one row at a time. And so that's the input shape into the model. Now, that in itself is one convolution. Okay. To convert it then into a dense layer, the next thing we would want to do is flatten it. All right. We'll come back and do max pooling and maybe a second convolution. I want to get a base model up here first. Okay, so we're going to flatten the layer. And that just stretches it out to 1D. And but see, that's after all these filters have gone into play. And so we'll do model.add, flatten. And then you don't really flatten, you can just leave it. Excuse me. Flatten, you can just leave. Like it just flattens it. You know. And then we have our output layer. We definitely want to show model summary so we can see it. And guess what? The rest of it should actually be the same because it's still a 10 output like numerical thing. So we can still use an optimizer of atom, categorical cross entropy, metrics equal accuracy. We change these to X and Y. And I want to shorten this to 20 so that we can get multiple models up. Okay. And we're going to evaluate an X test and Y test. So this is a base model. Okay. We just want to be sure that it works. Okay, we've got our first convolution in here. Let's go over it one more time. This is the key piece. What it's saying is 32 means, hey, let's find 32 filters, right? And so when this model is built, like the deep learning process, it's going to go through and try to optimize. It's going to try 32 random filters and say, oh, we got this many errors. Gradient descent calculus, let's adjust them based on the errors. It'll keep trying new numbers until it optimizes. Each of the filters is going to be a 3 by 3, okay? Activation functions means everything's just taking its positive value, and the input shape is essential. That's what each row of X has as the input. Then, after coming up with those layers, after those convolutions, and note that we add it to it. So like it's not just you come up with it, you transform the data and we flatten it out into one big layer. All right. And, you know, I want to do max pooling 2D also, but just showing you, going over again how this works. And then once it's been flattened, it's like just like before. Then we got the 1D, like a bunch of pixels. And so, hey, let's just like use a softmax to find them. Okay, let's give it a try. Usually there's an error when you do something new. If you get errors, don't worry. We'll find them. You can see that the convolution is with a lot of parameters. And that's why we want to use the max pooling 2D, because you're flattening out something that's like heavy dimensions. Okay, and so let's see how it does though with just the one convolution. You can see it's quickly hitting 99%. Bam, look at that. It's already at 100, dipping a little, right? And let's see, what's our test? 96.4%, outstanding. So with one convolution and one flatten, we deliver an awesome model. Is it overfitting? Yes. How do I know that? Well, because the error is 96.4%, but the accuracy is 100. And note that I got 100 pretty quickly, about 10 epochs. Okay, so we're going to expand upon this model next, add some more layers, and see how that looks.